Welcome back. In this video, we'll be talking about factoring polynomials. I have a couple of definitions there: monomials, binomials, and trinomials. Those are polynomials that have one, two, or three terms. The one thing I didn't define there is a term, and in a polynomial, the terms are separated by pluses and minuses. So for an example here, this x squared minus 3x plus 2, this would be an example of a trinomial because we have three terms: x squared, the negative 3x, and the positive 2. Those are our three terms for that polynomial. Now, if we were to notice that by taking x minus 1 and x minus 2 together and multiplying them, that would give us this polynomial, that means that x minus 1 and x minus 2, that they're both factors of that polynomial. And that's our goal here. Our goal is for any polynomial to find the factors. Now, at this point in our life, we're only going to be talking about factoring polynomials using factors that have integer coefficients. So we won't be interested in factoring things yet at this point where maybe a coefficient happens to be a decimal number or happens to be a root. So at this point in our life, when I say factoring polynomials, we're really only thinking using integer coefficients. And one thing that you'll hopefully remember from your previous mathematical days is that not every polynomial will factor, that there comes to be a point where you can't factor any further. And a polynomial that can't be factored is called prime. So an example here, x squared plus 1, that can't be factored, so you would say that that is a prime polynomial. Now, for all of these factoring techniques, they're sort of in the order from most straightforward, easiest to more complicated. And these are also in the order in which I usually think about them. Because when you're given a polynomial, you might have to use more than one technique to factor it. So the most straightforward one, the one that I always begin by asking myself is, can I find a common factor for a polynomial? And by common factor, I mean something that comes out of all of the terms from that polynomial, not just some of them. So as an example here, if you're looking at this polynomial, 6x cubed plus 15x squared plus 10, there is nothing that could be taken out of all three of the terms. If you're thinking, for example, about powers of x's, there are x's in the first two terms, but not in the last one, so there's no way to factor out any sort of a common factor that has an x in it. And even if you're thinking about just factoring out a constant, numbers that go into 6, 15, 10, there's no number except for 1 and negative 1 that does that. And here when I'm saying to factor something, factoring out a 1 is not really the most useful thing to do. So even though, yes, I suppose I could factor 1 out of everybody, I would say that this is something where a common factor is not really helpful. Now, on the other hand, these two examples of polynomials that I have here, these are ones where common factoring would help us. If we're looking at the example A, you can see that all three terms have m's in them. And if we're looking further, all three terms are divisible by 3. 3 happens to go into the 27 as well as into the 6 as well as into the 18. So when I'm factoring, I could factor out both a 3 and an m out of every term, leaving in the first term 9m cubed, leaving in the second term 2m squared, and in the last term leaving just 6. And we would want to check ourselves to ask the question of, could we factor any further? Does this polynomial factor any further? And we haven't talked about any other factoring techniques, but I'll just say right now that the answer to that is no, that actually doesn't factor any further. Now, one thing I do want to say about common factoring here, this example was me just taking a single term, a monomial, out as a common factor, but that may not necessarily be the only time you're doing common factoring. You might factor something more complicated than just a single term out. So if we're looking at this second example B, this is a polynomial. It doesn't quite look like it, but if you imagined expanding this out and expanding that out and combining all the terms, you would have a polynomial. But if I'm looking at how it's written currently, there are really two big terms. This first term, which is x plus 3 times x minus 4, and this second term, which is x plus 2 times x minus 4. And if I'm looking at both of those terms, they both have x minus 4 as a factor. So x minus 4 could be factored out of both terms. And that means that in the first term, there would be an x plus 3 left over. And in the second term, there would be an x plus 2 left over. So in other words, once we've factored out the x minus 4, what's left over should be 2x plus 5. Couple of formulas, one that you will definitely remember and the other two that you may or may not. We should hopefully all of us remember the difference of squares, that special product. That when we have one perfect square minus another, that can be written as, in this case, a squared minus b squared could be written as a plus b times a minus b. And we also have similar sorts of formulas for differences in sums of cubes. So for one perfect cube minus another perfect cube, or one perfect cube plus another perfect cube. We've got little shortcut formulas for factoring those. One thing just to mention about these, if you're using the difference of cubes formula or the sum of cubes formula, once we've taken that factor of either a minus b or a plus b out, what's left over, for the most part, typically will turn out to be something that's a prime polynomial, something that won't factor any further. One thing just to note here, even though we've got sums and differences of cubes, we only have differences of squares. We don't have any special product for the sum of two squares. Something like a squared plus b squared typically won't factor any further. You can maybe at most take out a common factor of a constant, but that'll be about it. So something like 16x squared plus 4, you could factor 4 out as a common factor, but that's as far as it's going to go. There's no special product for a sum of two squares. So for the first one, we have 27x cubed plus 8. And if I'm thinking about that for a minute, 27x cubed, 27 is 3 that's been cubed, and x cubed is x that's been cubed. So really, it's 3x that's been cubed, plus 8, and 8 is 2 cubed. So just to go back and look at our formula now, this is something where we have a perfect cube plus another perfect cube. In this case, if we're thinking in terms of our a's and our b's for our formula, here the a would be the 3x and the b would be 2. So using our sum of cubes formula, we would have 3x plus 2 times 3x squared minus 3x times 2 plus 2 squared. So just using my sum of cubes formula, and then simplifying what I have inside that bracket, 3x squared, which is 9x squared, 3x times 2, which is 6x, and 2 squared, which is 4. And if we take a look at what we have here, you can see that 9x squared minus 6x plus 4, there's no common factors that I can take out of that, and you'll be able to confirm towards the end of this video that actually that polynomial does not factor any further. For the one below, 81x to the 4 minus 16, we'll notice that 81 is a perfect square. It's 9 squared. And x to the 4 is x squared that's been squared. 16 is 4 that's been squared. So here we've got a difference of squares. I have 9x squared squared minus 4 squared, which factors as 9x squared minus 4 9x squared plus 4. And one thing, of course, which is going to be true as for the rest of our days is that when we're factoring, it's always going to be the question of, are we done? We'll have to ask ourselves, could we factor any of these factors any further? The 9x squared plus 4, this one does not factor any further. That's one perfect square plus another perfect square. Those sums of squares, they don't factor any further. But this 9x squared minus 4, 9x squared is the same thing as 3x that's been squared, and 4 is the same thing as 2 that's been squared. So we do have a difference of squares. That first factor, 9x squared minus 4, actually could be factored further as 3x minus 2, 3x plus 2. Okay, now we're getting into factoring polynomials that are quadratic. So polynomials where we have the highest power is squared, x squared plus an x plus a constant. There's two cases that we're going to be considering. One case will be polynomials where the x squared term is just x squared, no coefficient other than 1 in front. But we'll also be looking at cases where what if the x squared has a coefficient that's not 1? Now, for these kind, where it's just x squared, no constant in front of the x other than 1, this is the easy one for us to do. We just have to find two numbers that multiply together to give us whatever the constant term is, and then add up together to give us whatever the coefficient of x is. And once we found those two numbers, we're pretty much finished. Once we find those two integers p and q, then our polynomial factors out as x with the first number and x with the second number. And of course, the other nice part here is that if there aren't two numbers that have that property, if you cannot find two numbers that multiply together to give you c and add up to give you b, then that means that that polynomial can't be factored out with integer coefficients, which is kind of nice to know. So something like this, x squared minus 2x minus 35, we would need numbers that multiply together to give us negative 35, and these numbers would need to add up together to give us negative 2. And so if we're thinking about, well, what numbers multiply to negative 35, you could have 5 and 7, where one of them is positive and one of them is negative, or you could have 35 and 1, where one of them is positive and one of them is negative. If we're going through our options here, the only way to get two numbers to multiply to negative 35 and add up to negative 2 would be if our numbers were negative 7 and positive 5. Those two would add up to negative 2. They would multiply to negative 35, which means that our polynomial factors as x minus 7 times x plus 5. Now, if we've got a polynomial that has an even number of terms, then we can try using factoring by grouping. The idea behind factoring by grouping is that instead of taking a common factor out of the entire polynomial, we take common factors out of the first half of the terms and then take out a common factor out of the second half of the terms. And if we're lucky, if we've done things correctly, hopefully what will have happened is that what's left over for both the first half and the second half will be the same. In other words, we'll have a common factor that can now be taken out of everybody. One thing that I want us to keep in mind here, of course, is that when I say looking for a common factor in the first half of the terms and a common factor from the second half of the terms, you could always consider 1 or negative 1 to be a common factor. You could always factor 1 out of any one. So keep that in mind, that even if you're looking at things that don't appear to have common factors, they always do. You could always factor out a 1 if that's what makes it happen. So for this polynomial that I've got here, 12x cubed plus 8x squared minus 3x minus 2, I first ask myself, well, okay, are there any common factors that could come out of the whole thing? Could I find any value or any power of x that could be factored out of all of these terms? And the answer to that is no. So, okay, it's not a case of common factoring. This is also not a quadratic. We have a degree 3 here for our polynomial, so this is not something where I can use what I did on the previous slide. But this is something with an even number of terms. So the idea here is that I'll be factoring out of the first half of the terms some sort of a common factor, and I'll be factoring out of the second half of the terms some sort of common factor. So from the first two terms, 12x cubed plus 8x squared, I could factor out of those terms a 4, and I could also factor out an x squared. And so from the first two terms, if I were to factor out 4x squared, what that would leave me with would be a 3x in the first term and a plus 2 in the second term. So we factored from the first two terms. I want to now factor from the last two terms, and my goal is to hopefully get something that is the same left behind for both. Now, for the first two terms, it was positive 3x plus 2 that was left behind, and in my last two terms, I'm hoping to also have positive 3x plus 2 left behind. So if I were to factor out of those last two terms a negative 1, then that would leave me with 3x plus 2 left behind for those last two terms. So one thing you'll notice now is that originally we had four terms, 12x cubed, 8x squared, negative 3x, negative 2. Now we really have two big terms. One big term, 4x squared times 3x plus 2, and another term, negative 1 times 3x plus 2. So I'll be able to do some common factoring here, and the common factoring will be taking out that 3x plus 2. And that leaves 4x squared from the first term and negative 1 from the second term. So what's left over now? 4x squared minus 1. And if I wanted to, I could go one step further, because 4x squared minus 1, you might notice, hopefully you did, that is a difference of squares. 4x squared is 2x that's been squared. 1 is 1 that's been squared. So that last term, 4x squared minus 1, will factor out as 2x minus 1 times 2x plus 1. Okay, so now we're going to be talking about the little bit tougher case, the case where we're factoring a quadratic, but here where the coefficient for the x squared term is not just 1, where it's something else. Now there still is a little bit of a find two numbers game that we're going to be doing here, finding two numbers in particular that multiply together to whatever these coefficients multiply out to. And the two numbers that we're looking for add up to whatever that middle coefficient is. So that's similar to what we did before. The difference is that once we found our two numbers, then it's not just a case of jumping immediately to our answer. What we'll have is that our two numbers that we find will allow us to split that middle term up into two terms. So that we had something that originally had 3 terms, now we'll create something that has 4 terms. Once you have something with 4 terms, factoring by grouping is an option. Now, a fun fact with this is that if you do find your two numbers correctly, and if you correctly found the p and the q in question, then factoring by grouping will work. If factoring by grouping doesn't work at this point, then that means you didn't find the two numbers correctly, and go back and check your work. So let's see an example of this. So here I've got 5x squared minus 18x minus 8. First thing that I have to ask myself, as always, can I take common factors out of all of these terms? The answer is no. This isn't something where factoring by grouping will work yet, because it has an odd number of terms. It isn't a special product. This is a quadratic, but it's one where the first term, the x squared term, isn't just x squared, it's 5x squared. So when we're looking for our numbers, they're not just numbers that multiply to negative 8. Rather, the numbers that we're looking for need to multiply together to give us whatever the coefficient for the x squared term is times the constant term. So in other words, the numbers that we're looking for need to multiply out to whatever 5 times negative 8 is, or in other words, negative 40. And they need to add up to whatever the middle coefficient is, that negative 18. So I'm looking for numbers that multiply out to negative 40 and add up to negative 18. And I'm thinking about, well, which numbers multiply to negative 40? 20 and 2, one of them positive, one of them negative, that would do it. And if you were to take negative 20 and positive 2, they would multiply to negative 40, and they would also add up to negative 18. So we've done our little side work here. Now we'll actually use that to help us factor. So the idea is that these two numbers, the negative 20 and the positive 2, that's how we're going to split up that middle term. That negative 18x could be rewritten as negative 20x plus 2x. And that, of course, is true. Negative 20x plus 2x does mean the same thing as negative 18x. And now we've got ourselves something with 4 terms, so we can do factoring by grouping. Taking a common factor out of the first 2 terms, and hopefully when we take a common factor out of the last 2 terms, what's left behind for both will match. Now, the nice thing is here, if we found these 2 numbers correctly, if I haven't made a mistake finding my 2 numbers, then factoring by grouping will work. So I have kind of a little bit of a guarantee here. If I did find the right numbers, I will be able to do factoring by grouping. So let's do, out of the first 2 terms, I could factor out 5x, leaving an x and minus 4 behind. And remember that the goal is that for the next 2 terms, whatever I take out as a common factor, I want to have the same thing left behind. I want x minus 4 left behind, and that's possible if I were to factor 2 out of the last 2 terms. So now I can see that I've got really 2 big terms, 5x times x minus 4 and positive 2 times x minus 4. So x minus 4 could be taken out of both terms, leaving 5x from the first term and 2 from the second. So we have now 5x plus 2 times x minus 4. One last little add-on here. This isn't really so much a factoring technique, but it is something that's related to factoring. So if you were to look at this x plus b over 2 squared, if you were to expand that, if you were to take x plus b over 2 times x plus b over 2, and you were to multiply that out, you would have x squared, b over 2 times x, another b over 2 times x. We would have b over 2 times b over 2. That would be b squared over 4. You'd have x squared plus b times x plus b squared over 4. The reason that I'm mentioning this is the whole idea of what it means to complete the square. When we say completing the square, we're talking about taking something that's a quadratic and adding on to it a constant term so that what you have is a perfect square. So in this case, for this polynomial that we have here, x squared plus bx plus b squared over 4, that is a perfect square because it does factor out as something squared. So if you're sort of thinking about, well, what's the procedure here for how do we complete the square, the thing to notice, number 1, is that for whatever these first 2 terms happen to be, x squared plus something times x, that the term that we need to be the constant term needs to be b squared divided by 4, whatever b happens to be. And b squared divided by 4 is the same thing as taking b, cutting it in half, and then squaring it. That's usually how I think about it, how I create my constant term when I'm completing the square. I always think about whatever the coefficient of the x term is, cut that in half, and then square it. And you'll notice that when you get your perfect square, the perfect square is x with whatever the coefficient was cut in half. So if you're thinking about something like this, x squared plus 6x, if we were completing the square or wanted to complete the square, the constant term you would need would be taking this positive 6, cutting it in half, and squaring it. So positive 6, cutting it in half, that gives you 3. And 3, when you square it, that gives you 9. That means you would have something that would be a nice perfect square. So if we had x squared plus 6x plus 9, not only would that be a perfect square, but it would factor out as x with half of this coefficient squared. And in fact, you can check this out, that x plus 3, if you do square it out, it does give you x squared plus 6x plus 9. So when we're completing the square, that's our idea. We have x squared plus some constant times x. We'll take that constant that's in front of the x, cut it in half, and then square it, and that'll allow us to complete the square. So for the first one, we have x squared minus 10x plus mystery number. So the constant that we need is found by taking that negative 10 and cutting it in half. And negative 10, if you cut it in half, that gets you negative 5. And negative 5, if you were to square it, that gets you 25. So 25 is the constant that we need. Taking our coefficient of x, cutting it in half, and then squaring it. And as far as how does that factor, that factors as x with half of this coefficient, so x minus 5 squared. And in fact, you can check to see that if you were to multiply out x minus 5 times x minus 5, you would get x squared minus 10x plus 25. Same thing with the last one. Sometimes the coefficient of x doesn't divide by 2 nicely, and that's fine. It doesn't have to always be nice numbers. So for something like x squared plus 7x plus mystery unknown number, the coefficient for the x is 7, and if we cut 7 in half, we have 7 halves. And if we were to square 7 halves, we would get 49 over 4. So x squared plus 7x, the constant term that we need to complete the square, is 49 over 4. And this would factor out as x with half of this coefficient, so plus 7 halves, whole thing squared. And again, you can check to see that if you were to multiply this out, x plus 7 over 2 squared, that would give you that polynomial x squared plus 7x plus 49 fourths.